acid-base theories. First theory that we're going to be amending this year is the Arrhenius theory of acids and bases. And this is maybe what you learned last year. So basically what he said was that an acid is a substance that dissociates in water to produce hydrogen ions. And a base dissociates in water and produces hydroxide ions. So that is the old Arrhenius theory of acids and bases. However, things like ammonia here, when they are added to water, they didn't follow that theory. So will ammonia be an acid or a base according to Arrhenius' theory? So ammonia has no OH ions. So according to Arrhenius' theory, it cannot be a base. However, when you put ammonia in water, it forms a base. So this theory had to be changed. So ammonia, when it goes into water, you end up producing hydroxide ions. Now ammonia doesn't have any hydroxide ions, so bases do involve hydroxide ions, but they don't necessarily have to be in the base itself. So two guys came up with a new theory that incorporated this sort of behavior of bases. They stuck with the same-ish definition for an acid. So they still said, so this is Bronson and Lowry, they said that an acid is a substance from which a proton, or hydrogen ion, can be removed. So think of these guys as being proton donors, things that give off protons, hydrogen ions. To deal with all bases, even those that don't have hydroxide, they changed the definition of what a base was. So it didn't have to have a hydroxide ion, though it could, but it didn't have to. They instead said that a base is a substance that can remove a proton from an acid. So a base now is a proton acceptor. Anything that accepts hydrogen ions, protons, we will refer to that as a base. So if we go back to our previous equation here, if we look at what ammonia has done, there it is at the beginning of the reaction, and here it is as a product. The difference between those two is one positively charged hydrogen ion. So ammonia has accepted a proton to become ammonium. That makes it, according to Bronson and Lowry, a base, a proton acceptor. Now, we're going to be talking about hydrogen ions, protons, a lot. What we need to realize is that it's kind of a lazy way of just thinking about the protons. These are all going to be in aqueous solutions, and as soon as you put a proton into an aqueous solution, it bonds to one of the water molecules. So you take the hydrogen ion and it gets stuck onto one of the water molecules, and you get what's called a hydronium ion. So really, every time we're talking about protons, they get bonded to water, and now we have hydronium ion, but often we're lazy and we're just going to talk about the hydrogen ion itself as if it weren't stuck onto a hydrogen ion. So like Arrhenius said, a Bronson and Lowry acid must contain hydrogen, so if it's going to be donating hydrogen, it's got to have some in there. However, anything that accepts protons can be a base. Hydroxide will do it. It'll accept protons, but other things can do it as well, like ammonia. So an acid-base reaction involves the transfer of a proton. That's essentially what an acid-base reaction is. You have someone donating a proton, you have someone accepting a proton. So HCl, everyone knows that one as an acid. When you put it in water, it acts as an acid. And the reason is, if you look at your HCl molecule, it will take that hydrogen that's attached to it and it will stick it onto a water molecule. And this produces hydronium ions, and it leaves behind a chloride ion. So the chloride ion is now by itself, and the water, which has picked up the hydrogen ion, is now a hydronium ion. So that's what happens with HCl in water. So a couple definitions to talk about these reactions. We're going to talk about conjugate acid-base pairs. So the two substances that are related by the transfer of proton, that is a conjugate acid-base pair. So if we go back to this reaction, if we look at water here, and we look at hydronium here, the only difference between water and hydronium is a hydrogen ion. So we're going to see that later in our definitions. A conjugate base is the particle that is left over when a proton is removed from an acid. So if you start with something that has a proton, let's call it HX, it can act as an acid as long as it lets go of that hydrogen. So if it lets go of that hydrogen and it goes somewhere else, What's left over is the particle that's left over when a proton is removed from the acid. So that thing that's left over, that would be called a conjugate base. A conjugate acid is the particle that results when the base receives a proton. So let's say this is the acid here and it has a proton, and it gives it to, I don't know, some other thing over here called Y. And when it becomes part of that, so now it would be the proton plus the original Y. I'll put a positive charge on it because the proton came with a positive charge. So this thing here that has accepted the proton, that is the conjugate acid. So let's look at how these work in an equation. So let's say we had hydrogen bromide reacting with water to form hydrobromic acid. Identify the conjugate acid base pairs. So just like the HCl example before, if we took hydrogen bromide and wrote the balanced chemical equation for it reacting with water, we would take your hydrogen bromide and your water molecule, and if this is to be an acid, it's going to take its proton and it's going to give it to the water molecule. So what you end up with is a hydronium ion. Used to be a water molecule, picked up a proton, now it's a hydronium ion, and the thing that's left from the hydrogen bromide is just a bromide ion. So that's the balanced chemical equation. Now let's start labeling things. So first off, let's look at the reactant side. We want to identify the acid and the base. And remember, the thing that donates the proton is the acid, the thing that accepts the proton is the base. So hydrogen bromide here is the thing that has the proton, the hydrogen ion, and it is the one that is going to donate it, leaving it behind without it. Water here starts out as normal water and ends up as hydronium, so it has obviously accepted a proton, so it must be, the water must be acting as the base. So the hydrogen bromide donates, the water accepts. We label hydrogen bromide the acid, the donator, and water the base, the acceptor of the proton. And we see what they become at the other side of the reaction. That's where other labels come in. So the product side, we identify the particle that was the acid, and it now doesn't have that proton, it's donated it. That is the conjugate base. The particle that was the base and now has accepted a proton is called the conjugate acid. So if we look at our equation, we have hydrogen bromide as our acid, water as our base. Now hydrogen bromide became, it let go of the hydrogen ion, and now it is just a bromide ion. So the thing that donates the proton is the acid. What it becomes on the other side of the reaction is the conjugate base. The acid becomes the conjugate base. The base here has become hydronium ion. It has accepted a hydrogen in order to do that. So the base accepts a hydrogen, and the thing that it becomes is a conjugate acid. The base becomes the conjugate acid. And if you think about it, if they wanted to go back the way they were, if bromide wanted to go backwards and become hydrogen bromide again, what would it have to do? It'd have to pick up a hydrogen. That's the only way to go backwards. The things that pick up hydrogens are bases. If hydronium here wanted to go backwards, it would have to let go of a hydrogen. And what sort of things let go of hydrogens? Acids. So the base becomes a conjugate acid, the acid becomes the conjugate base. These partners here we can call conjugate acid-base pairs. So the base and the conjugate acid, that's a partner. The acid and the conjugate base, that is another pair.